Hi, my name is Esther Sumner and I'm a lecturer in sedimentology at the University of Southampton, and I'm going to tell you about giant avalanches in the deep sea. So I thought I'd start this mini lecture by taking you back in time to 1929 and telling you about the mystery of the Grand Banks. So in 1929, the state of the art in transatlantic communications were copper cables that were laid on the floor of the ocean. And so here you can see a map from that era, and on one side of the map we've got North America, on the other side of the map we've got Europe, and hopefully you can make out these black lines, and these are representing some of those cables on the seafloor. So you can see that lots of those cables come onshore North America in Newfoundland, and they cross an area just offshore Newfoundland called the Grand Banks. This is a diagram of the seafloor, the slope of the seafloor off the Grand Banks. It's very vertically exaggerated, so that means it's very stretched in the vertical axis. But what it's showing you is those black dots are showing you the locations that those cables cross the seafloor. So on the 18th of November 1929, a massive earthquake rocked the Grand Banks, and when that earthquake occurred, all of those cables that I've shown highlighted with those red stars, they all broke instantaneously when that earthquake occurred, causing lots of shaking. But then something quite strange happened, because in the hours following the earthquake, cables in progressively deeper water got broken, and those cables I've shown with these blue stars. So 13 hours after that earthquake occurred, a cable was broken over 800 kilometres from where that earthquake occurred. And at the time, this was a big mystery, because at the time, the deep sea was considered to be this very quiet place where nothing really happened, yet on this occasion in the 1920s, they've got evidence of these thick copper cables getting broken right out in the deep sea, and they didn't really understand how that had happened. So for us to begin to get an understanding of what happened, we have to fast forward to 1952, and I'm going to introduce these two characters who are Bruce Heezen and Maurice Ewing. So Heezen and Ewing are two eminent geoscientists of the 20th century, so you may or may not have come across them for their work on plate tectonic theory, but in 1952 they weren't thinking so much about plate tectonics, they were thinking about what caused these cables to break off the Grand Banks. And so what Heezen and Ewing did is they went and took a look at the reports written by the cable companies who went out to mend those cables. So this is a cable ship from the 1920s. So these ships were going out into the Atlantic, they were laying these cables on the seafloor, and when these cables got broken, then those ships would go out to mend those cables. Now when Heezen and Ewing looked at the report written by the cable company that went to mend these cables, they found that the report said all of those cables that broke instantaneously when the earthquake occurred, they were all exposed on the seafloor. Whereas the cables that broke in the hours following the earthquake in deeper water, they were actually buried by a thick deposit of sand and mud that could be many metres thick. So what Heezen and Ewing proposed had happened is that when that earthquake occurred and it caused lots of shaking, then it caused lots of slumping of seafloor sediments in this region, which caused the breaking of those cables if they didn't get broken by the initial shaking. But what happened is those slumped sediments, as they started to slide down slope, they started to entrain more seawater into them, so they became more dilute, more turbulent, and they generated basically a very mobile sediment avalanche that then rapidly progressed out into deeper water. And that's what and that sediment avalanche eventually deposited its sediment load on top of those cables, and that's why they got buried. So in subsequent years, people have actually sort of revisited this data set, so it's a very important data set for geologists. And they've thought about actually how far apart are these cables, at what time did the cables get broken, and from this they've been able to estimate that this flow was going at speeds of up to 20 metres per second, so really, really fast. What's even more impressive about that is in the deep ocean, you know, some of the gradients this sediment avalanche was travelling on were actually less than a 1 degree slope. So to put that in some kind of context, I believe that Lord's cricket pitch has a steeper slope than that on it. So they're basically travelling across very flat bits of seafloor at many metres per second, ripping up these cables. So I've told you about a sediment avalanche in the deep ocean in the 1920s breaking cables. So why should you care about sediment avalanches in the deep sea in the present day? So there's two maps in this slide. The top map is the map that I've already showed you, showing those copper cables on the seafloor in the 1920s. And this bottom map is a map of the present day, showing you where fibre optic cables are on the seafloor. So what these fibre optic cables are for, they're basically for transmitting data around our planet, so they underpin things like the internet. So if you were to send an email, say from somewhere in Europe to somewhere in North America, I think a lot of people think that that email or the data of that email would somehow sort of fly through the ether, bounce off a satellite, come back down to Earth. That's not the case. Actually, 9 times out of 10, that data would be sent by one of these fibre optic cables. So it still matters that we've got these sediment avalanches on the seafloor, which basically every so often will rip a load of these cables out, slow down the internet, and the internet obviously underpins our daily lives and things like financial markets. So ideally we want to understand what these flows look like and better understand how they affect the seafloor and the hazard that they pose. There's also all sorts of other infrastructure today on the seafloor, so things like oil and gas pipelines that we definitely don't want to get broken. And then these sediment avalanches are important for a whole host of reasons. So another reason that might be of interest is that they're basically how we get lots of sediment from land out into the deep ocean. And we're not just transporting sediment, we transport anything that's incorporated within those sediments. So that could be things like pollutants, and of great relevance in the present day is it could be things like microplastics. So these sediment avalanches are very relevant to understand in the present day. So what do these seafloor sediment avalanches actually look like? Well, they're somewhat difficult to study in action on the seafloor, and that's because they're occurring in an inaccessible location, so they're occurring on the seafloor beneath potentially many kilometres of water. They're pretty unpredictable in terms of where they're going to occur, or certainly lots of them are unpredictable. So for example, the example I showed you for the 1920s, that was triggered by an earthquake. We couldn't have predicted exactly when and where that earthquake would occur, so we couldn't have predicted exactly when and where that sediment avalanche would occur. Some sediment avalanches are a little bit easier to predict when and where they'll occur because they can be triggered by actually a whole host of different mechanisms. But another problem in studying these flows in action on the seafloor is they're also very destructive, so it can be quite tricky. You put something in their path to measure them, and potentially the flow destroys those instruments. So I'm going to start by showing you how we were trying to understand these sediment avalanches in the 20th century before coming forward to the present day. So the main data set that we actually have about these sediment avalanches are the deposits that they leave behind in the geological record. So this is a hillside in the Italian Apennines. This is somewhere I've done quite a lot of fieldwork in the past. And what you're looking at is basically a slice of ancient seafloor. So all these horizontal layers that you can see, these are basically the deposits of sediment avalanches that traversed the seafloor many millions of years ago. So the layers that stick out tend to be quite sandy, and the layers that weather in are quite muddy. We can hike up to these layers and take a look at them in more detail, and we can understand things like what size of sediment could these flows carry. So, for example, we see, in this case, you can see sands, but we also see, for example, gravel and cobbles in there, and then lots of mud in between. We can also look at any clues that we have within these rocks, so things like sedimentary structures, so things like ripples and laminations, because they tell us something about the dynamics of the flow as it deposited those sediments. But this is a really, really tricky thing to do, right? Because effectively what you're trying to do is you're trying to infer the dynamics of a flow that no one's ever really observed from the deposit it left behind in the geological record many millions of years ago. So another way that we've gone about studying these sediment avalanches is to generate small-scale sediment avalanches in the laboratory. So I'll show you a video of one of these sediment avalanches. I've actually taken this video from YouTube. It was made by the geology department at Western Washington University in the United States. There are loads of fantastic videos of sediment avalanches in the laboratory and also in the real world on YouTube, so I thoroughly recommend checking those out. So in the video we're going to watch here, this is basically a tank of water and somebody's releasing a mixture of sediment and water to represent the avalanche into that tank. So here you can see that sediment avalanche moving down slope and moving across the floor of the tank, and hopefully it actually looks quite familiar to you, because it should hopefully resemble or remind you of a snow avalanche. So most people know what a snow avalanche looks like, and actually snow avalanches, pyroclastic flows on volcanoes, and these sediment avalanches in the deep sea are all in the same big family of flows. They're called gravity currents, and so they do share some dynamics between them. So there are some similarities among those different types of flows. So we can generate small-scale sediment avalanches in the lab, but again, this isn't ideal because they are small scale, so they're going at centimetres per second rather than metres or tens of metres per second, and they can only carry very fine scale sediment rather than the much larger sediment that we find in these flows on the seafloor. So whilst experiments can be useful in understanding something about the dynamics of these flows, they have their limitations also. So ideally what we want to do is we want to go out and measure these sediment avalanches in action on the seafloor. And so that's what we can now do. So in the final part of this talk, what I want to just introduce you to is some of the technology that we now have available to measure these sediment avalanches on the seafloor. So the first thing we really want to know before we go about actually measuring sediment avalanches is what the seafloor looks like. And we now have great tools to do that. So we have different types of underwater robots. So for example, this yellow submarine here, this is called an autonomous underwater vehicle, or AUV. It's an unpersoned vehicle, so there's nobody inside it. You basically pre-program it to go and fly around the seafloor on a mission. And actually what these little yellow submarines are really good at doing is making high resolution maps of the seafloor, which is what you can see being done here. We have other types of underwater robots. So this is a remotely operated vehicle, or ROV. Again, it's an unpersoned underwater vehicle. There's nobody inside it. But this time, rather than pre-programming it, it's actually attached to the ship by a cable, and commands are sent to it in real time through that cable. So if you're on board the ship, the people controlling the vehicle, it looks a bit like they're playing video games, sort of steering this vehicle around the seafloor. But you can go, for example, you can explore the seafloor, and you can also pick up samples, so rock samples, sediment samples. So you can learn a lot about what the seafloor looks like using this technology. But if we want to understand these sediment avalanches, then we need slightly different pieces of technology. So one of the main pieces of technology we now use to measure these sediment avalanches are moorings. So this is a cartoon of a mooring here, and a mooring is basically a big wire that we attach equipment to. So at the bottom of this wire we have a big weight, so this is quite often train wheels, and at the top of the wire we have a load of flotation, so we're trying to keep that wire vertical in the water column, and then we can attach different instruments to it. So for example, we could attach a sediment trap that's going to collect samples of sediment from the moving flow, or we can attach more advanced pieces of equipment, so things like acoustic Doppler current profilers, which measure the velocity of the flow. So this is an acoustic Doppler current profiler. It would be looking downwards at the seafloor, and as the sediment avalanche went underneath, it would measure a vertical profile of the velocity structure through that flow. Now these moorings are great if you're using them where the flows aren't too ferocious, so maybe if you're quite a long way from where that flow started out. But if you're using them sort of where the flow is going really fast, then they tend to get destroyed. And so we have other equipment to use in those locations. So for example, we have things like these intelligent boulders. So this intelligent boulder, or smart boulder, is about the size of a basketball. And inside that basketball we have an accelerometer. And so that's measuring the orientation of the boulder. So it's actually the same type of accelerometer as you'd find in your smartphone. And so in your smartphone, that accelerometer is basically telling the phone which way up it is, so that it can orientate the picture correctly, whereas we can download the data about how are these boulders moving. Are they sort of sliding along in the flow, or are they tumbling along in the flow, and where do they start and where did they end up? So we live in pretty exciting times for actually measuring these flows in action on the seafloor, and certainly from our preliminary results, they've actually really changed our view of what these sediment avalanches look like. So for example, I showed you that video, and in that video we saw that small laboratory sediment avalanche basically moving along the floor of the tank. Whereas actually using these types of technology, what we've learned is actually these sediment avalanches can cause whole-scale remobilization of the seafloor to many meters depth. And so rather than their flow moving across the seafloor, we're looking at the whole seafloor moving with the flow. And so that obviously has big implications when you're trying to protect infrastructure that you've built on the seafloor. So I think I'll leave it there. Hopefully I've introduced you to the idea of these sediment avalanches in the deep sea. Hopefully I've given you some reasons why they're important to better understand. And hopefully I've excited you with a bit of the technology which we can use in the present day to study them. So thank you for listening.